This video provides an introduction to continuity. We've previously divided a continuous function as a function y equals f of x is continuous if there are no holes or jumps that occur and the graph can be drawn without picking up your pencil. That was the definition that we used throughout college algebra. Well, we're going to beef that definition up. A function y equals f of x is continuous on an interval if f of x is continuous at every point in the interval. A function y equals f of x is continuous at an interior point a of its domain if the limit as x approaches a of f of x is equal to a. So it's continuous if its limit and its actual value are one and the same. We have definitions for left and right hand continuity as well. A function y equals f of x is left continuous at a point a if the limit as x approaches a from the left of f of x is equal to f of a, and a function y equals f of x is right continuous at a point b if the limit as x approaches b from the right of f of x is equal to f of b. A function is discontinuous if there are holes or jumps that occur and it cannot be drawn without picking up your pencil. The points where the holes or jumps occur are called points of discontinuity. I see my text is slightly off in this diagram, but we can still look at it. So this point A would be said to have right side continuity because it's continuous up to the right. This point B has continuity from the left because it's continuous as it approaches up into the left side. And then the point in the middle is continuity at an interior point. So let's take a look at this graph, and we want to determine if f of x is continuous at x equals -2, x equals 0, and x equals 3. And we want to do a little more than say, oh, I had to pick up my pencil to trace it. We want to talk about limits when we're answering these questions, right? Calculus answers when we're in calculus class. Oh, let's start with x equals -2. So that's happening right here. Clearly discontinuous, right? Huge jump that we would have to pick up our pencil for. But let's give a calculus reason here. F of x is discontinuous at x equals -2 because the limit as x approaches -2 of f of x does not exist. Right? If we go back and we look, it says that it is continuous on an interior point, which that certainly was because it wasn't on the far left or the far right side of the total graph. It says that the limit as x approaches a of f of x has to be equal to f of a. And the limit doesn't even exist because the left and right hand limits don't match. So not continuous there. Next, we want to check at x equals 0 right here. Clearly continuous. There's no breaks or holes or anything like that, but we want to give a calculus reason. F of x is continuous at x equals 0 because the limit as x approaches 0 of our function f of x is equal to f of 0. Right? The limit from the left and right side are both equal to positive 1, so the limit as x approaches 0 in general exists and is equal to 1, and we see we have a closed circle right there at 0, 1, telling us the y value at 0 is also 1. So because the limit and the actual value are the same, it's continuous. Lastly, we want to look at x equals 3. We can already tell that it's not continuous because I have that hole there. F of x is discontinuous at x equals 3 because although the limit as x approaches 3 exists, the left and right hand side are both approaching 0. Although the limit exists, the limit and the actual point value are not the same. Therefore, it's discontinuous. So it's nice to use what we already know about continuity to know what the answer is ahead of time, but we need to be able to back it up with calculus reasons. There are different types of discontinuity. First up is a removable discontinuity where we just have a hole in the middle of our graph. We might have an infinite discontinuity where our graph is approaching some type of asymptote. There is oscillating discontinuity where our graph is just oscillating so fast that it can't, it's not sitting still. So we can't say it's approaching a particular place. And then our last type is called jump discontinuity. You may or may not have seen this function before. We don't discuss it in college algebra. This is called the least integer function. Sometimes it's called the floor function. Least integer function is the more technical. And with this function, what's happening is you're always rounding down to the least integer. So in between 0 and 1, like we have this x value of 0.8, but we're just rounding down to the least integer, which would be 0. And then in between 1 and 2, even if we're at 1.99, we're always rounding down to the least integer, so we round down to 1, and that's why we have a y value at 1. This is how they have it denoted. I've seen it denoted this way as well, where you just have the little bars on the bottom. I like that notation because then it reminds me to round down. There's another function that's similar to this called the greatest integer function, and here you're always rounding up. So it's the greatest integer function, or sometimes it's called the ceiling function. And it's denoted very similarly. It would look like, let me use g of x. G of x is equal to, but the little bars are like at the top. I always feel like that gives me a visual cue to know that I'm rounding up. So that's our introduction to continuity. We'll talk about the continuity test next.